Okay, let's talk a little bit about the cell potential, or the EMF. That's going to end up being voltage. So the flow of electrons from anode to the cathode is spontaneous in a galvanic or voltaic cell. And that is, electrons flow because the cathode has a lower electrical potential than the anode. So that potential difference measures the tendency for the electrons to want to flow the way that they do, and we can measure that in volts. That's not the amount of current, it's the tendency for the electrons to want to go from one place to another. If you want to measure how much electricity, you have to do that in amps. Volts just measures the direction of the spontaneous flow, or how much it doesn't want to go the other way. But the cell potential, E cell, is the voltage for the cell. And if you got a 1 molar concentration solution, 25 degrees Celsius, those are standard conditions. If a gas happens to be involved, which is not common for the types of cells we're talking about, you need 1 atm, but we'd call that the standard cell potential, so we call it E standard cell, using that same superscripted circle for the standard notation. And the way we do that is we create a table of standard reduction potentials, which is a measurement of half of the cell. So how do you measure half of a cell? You're going to use a reference, but they are introduced in Appendix E of your textbook, and I've got a table of those right here. That's sort of an excerpt from that, and notice they're measured relative to what we call standard hydrogen electrode. So we say, just for reference, that standard hydrogen electrode has a reduction potential of 0, and therefore half of the reaction is 0 if you measure it relative to standard hydrogen electrodes. Whatever voltage you read is the measurement of the other half. Could we have picked a different electrode? Sure. A lot of times they do that to indicate activity of a metal. Traditionally speaking, a metal is considered active if it were more active than hydrogen. That is, it would displace hydrogen gas from an acid. And so that's sort of the reasoning. And that electrode is kind of complicated experimentally, especially if you're just starting out. And so we won't really use that one in the lab, but we will certainly make reference to it. Those things with a big positive reduction potential are things that would rather be reduced in a redox reaction. They get smaller and smaller to where you see 0 there for their standard hydrogen electrode redox. And then these things that are negative are things that would rather be oxidized relative to standard hydrogen electrode. The bigger and more negative, the more likely it is to want to be reduced. Think of it like an activity series from first semester. If you want a positive voltage, that is, you want a galvanic or voltaic cell, the cell potential has to be 0, so you want the thing that's being reduced to be the cathode, that is the thing with the biggest and most positive reduction potential to be the cathode, and something less positive or negative to be the anode, if you want a galvanic or voltaic cell. So the SHE is a standard hydrogen electrode, and again, it's a complicated electrode. And it consists of a platinum electrode in a tube placed in 1 molar H+ solution. The H2 is bubbled through the tube, and so we would indicate that 2 hydrogens in 1 molar acid solution reacts with 2 electrons to form hydrogen gas at 1 atm of pressure. By definition, we say that standard reduction potential is 0. And so we can get the standard reduction potentials. The standard potential of the cell is equal to the standard reduction of the cathode, which is where the reduction actually takes place, minus the standard reduction potential of the anode, which is actually an oxidation, but we compensate for that by subtracting. So if we look at that, here is, instead of zinc with copper like we had in the previous video, this is zinc with standard hydrogen electrode, and we see that it has a voltage of 0.763. And so if that's the cell potential, and standard hydrogen electrode is 0, so that would be the reduction, so it's going to be minus the oxidation. And so we would say that the standard reduction potential for the zinc electrode is a negative 0.763. Because you have to flip the sign because it's actually an oxidation. The 0.763 would actually be the oxidation potential, but if I want the reduction potential, I have to flip the sign. And so the reaction we're looking at going on in the electrode is the oxidation of the zinc to form zinc plus 2 and 2 electrons. And so if we look at that relative to standard hydrogen electrode being the cathode, you put in 0.76 volts, which was the cell potential, equals 0 minus the E standard reduction for the anode. And just like I said, the E standard reduction for the anode is a negative 0.76 volts. And so we would write that reaction then as a reduction, say zinc 2 plus 2 electrons forming zinc metal. E standard reduction negative 0.76 volts. Notice everything in the appendix and in the table I showed you just before, all of that was in reduction potential. So all the reactions are written as reductions. If you're actually intending that reaction to be an oxidation, I need to flip that reaction around and I need to change the sign on the voltage. Or in our case, I use subtraction in the formula, which serves to automatically change the sign. Some different books will do that formula different ways. I subtract the reduction potential so that it automatically changes the sign. So since the E standard reduction is a negative 0.76 volts, we can conclude that the reduction is zinc 2 plus in the present standard hydrogen electrode is not spontaneous, but the oxidation of zinc with standard hydrogen electrode is spontaneous. And so to balance, and stoichiometry doesn't affect it. If I said 2 zinc plus 2 plus 4 electrons goes to 2 zinc metals, the reduction potential is the same. Yes, more electrons are transferred, but this, remember, voltage is the tendency for electrons to go from one place to another, not how many. So if E standard reduction is greater than 0, then it's a spontaneous reduction relative to the standard hydrogen electrode, or SHE. And the reactions with a negative reduction potential or spontaneous oxidations relative to the SHE. The larger the difference between those reduction values, the larger the E cell will become, either in a positive or a negative direction, depending on whether you have it set up favorably. If you end up with a negative cell potential, but you want a galvanic or voltaic cell, your electrodes are backwards, just switch the wires and you'll be set. So if you want it to be galvanic or voltaic, the E standard reduction is going to be more positive or at least less negative than that of the anode. You want those values to be biggest and most apart if you want it to get a large voltage. Noting the equation where you're taking the difference between those reduction potentials to get the cell potential. So a positive E cell represents a spontaneous or cell where you got a galvanic or voltaic cell. A negative E cell represents a non-spontaneous cell, or that would be an electrolytic cell, which we'll talk about maybe a little later. But we want that difference to be as big as possible if I want the large positive voltage. And so we can see that there, the bigger and more positive the reduction potential, and the smaller or more negative the anode, the bigger that E cell is going to be. And so E standard reduction is stronger the oxidizing agent, the more negative the standard reduction, the better the reducing agent. So if it's big and positive, it's going to be easily reduced and therefore an oxidizing agent. If it's more negative, then it's going to be more easily oxidized and therefore a better reducing agent. So which substance is the best oxidizing agent? We need to look. Oxidizing agents are things that would tend to be reduced. So hydrogen, H2, is already in a pretty reduced form. It's unlikely to go to hydride in aqueous solution, so we can rule B out. Chlorine likes to be reduced. Nickel and copper ions can be reduced. It's more likely that chlorine has the bigger, more negative reduction potential. If you look that up in Appendix E, for chlorine, you end up with a more positive number. Chlorine is a positive 0.136. Copper is decently easily reduced. And so if I go to the camera, and I stop the share momentarily, and we go to the camera, we can see chlorine is in there. And it's the 1.36. Copper is decently easily reduced. That copper 2 reducing is 0.34. If I move the camera down, you can see it right there with my finger. And then nickel's all the way over here, a negative 0.28. And so we can see that, and hydrogen we know is 0, so it's not going to be it anyway, and it's already in its more reduced form. So we can say the chlorine is going to be the most easily reduced, then the copper, and then the nickel, and then the hydrogen's already reduced, so it's sort of a moot point. So going back to the presentation, our answer would be C, and it would be the chlorine. So in a spontaneous cell that is a galvanic cell, we want that difference to be, as big as possible, but we can make it more generic. Instead of cathode anode, we can say reduction process and oxidation process if we want to look at a particular reaction being spontaneous or not. Even if it's not a cell per se, we can look at it and see what that redox would be, spontaneous or not. And it helps us understand that activity series from the first semester course. So let's look at E cell relative to calculating it from the appendix. And so we got a copper being oxidized, and it looks like a silver is being reduced. We need to look up those half cell potentials. So going back to the data table, we can see, well, we already talked about copper, but where's silver? Silver's right up here top, it's 0.8. So it would rather be reduced relative to copper down here, which is 0.34. So that is okay, actually. So if we look at it, I've got it all written down for the sake of time. We pulled those values out of the table. We can see that the silver is being reduced in the reaction, and in fact, it is written correctly as is. The silver would rather be reduced compared to the copper. So our E standard for our cell is equal to the E standard reduction for what's actually being reduced. In our case, the silver would be our cathode, or a reduction process, minus the E standard reduction for our copper, which would serve as our anode. And so we end up with 0.80 volts minus 0.34 volts. And we would just run that through our calculator. Now we'd get a cell with a positive 0.46 volts. And we could conclude, since that voltage is positive, that that would be a spontaneous or a galvanic or voltaic cell. So let's look at one more problem. And we'll look at this aluminum being the anode, where zinc is the cathode according to this notation. We're going to write the anode, the cathode, the overall cell reactions just to get practice writing the reactions. We'll use Appendix E to calculate the self-potential for the cell. And then we'll determine whether the reaction is spontaneous or not based on the voltage we calculate. So I've copied all that over. I've even went ahead and gotten the cell potentials in advance. So if this is my anode, we're going to write it as an oxidation. So Al solid reacts to form Al3 plus aqueous plus 3 electrons. The zinc's written as the cathode, so it's the reduction. So we're going to say Zn2 plus aqueous plus 2 electrons forms Zn solid. So that's the anode, the cathode. We need to get the overall, but I've got to make these electrons match. So I'm going to multiply this whole reaction by 2. This whole reaction is going to get multiplied by 3 to make the electrons match. And when I do that, I'd end up with 6 electrons total and it would cancel. So I'm end up with 2 Al solid plus 3 Zn2 plus aqueous reacts to form 2 Al3 plus aqueous plus 3 Zn solid. Now remember, the stoichiometry does not affect the E standard for the cell. So we want to calculate that E standard for the cell now. It's going to be the cathode, which will be our zinc reduction. For the zinc minus the E standard reduction for the aluminum. So it'll be negative 0.76 volts. It'd really better to not have a negative here, but if you do, you want the smaller of the two negatives. And so we're going to subtract a negative 1.66 volts. We'll still end up with a positive number because this is bigger and more negative, and we're subtracting. So we're going to quickly do the subtraction. And we get 0.90 volts. We're still getting a positive number. So to answer that last question, this is a spontaneous reaction. Which means I could form a galvanic or voltaic cell out of it.